Today we're starting at chapter 10, which is mostly involved with logarithms. And what you need to know when you remember all the way through this, the compass to guide you through this chapter is that a logarithm is an exponent. With that in mind, we need to talk a little bit more about exponents before we get into logarithms. And today we're covering state standard number 12. You need to know how to use fractional exponents. And then later in the chapter we're going to understand solving exponential functions and using those functions to solve problems involving exponential growth and decay. But before we get to that, let's first of all look at our strategy, and that is we've got to understand what a rational exponent is. We have to know the definition of it, and we have to be able to know how to apply it to simplify and solve equations. And as we jump into that, I think it would be a good thing if we took a look at some of the properties of exponents that we've learned already, just as a reminder. So here's a reminder, courtesy reminder. If you are multiplying and the bases are the same, you keep the base and add the exponents. Very important you remember that. Here's another reminder. If you are dividing and the bases are the same, you keep the base and subtract the exponents, numerator minus denominator's exponent. Also recall that if we had a product, a times b raised to some power m, that we could say that's the same as raising the first factor a to the m power, the second factor b to the m power. Next one we need to recall is that if you have a base raised to a power, and that in turn is raised to a power, you keep the base, don't change it, but you multiply the exponents m times n. And we've also learned that if you have a fraction raised to a power, you can raise the numerator to that power and raise the denominator to that power. We also recall that anything to the 0 power equals 1. Now, just a thought here, since these are equal signs and these are properties, we not only need to know them from left to right, as they are written here, but we should be able to go from right to left this chapter as well. All right, and the other one we need to cover that we're reminding you what it is that what a negative exponent is all about. Remember, if you have a negative exponent, that means take the reciprocal of the base. So if the base is a, that's 1 over a, and then we're going to raise a to the positive exponent. So a to the negative m power is 1 over a to the m power. So those are our reminders of our properties of exponents. But now we need to get on with the definition of understanding the meaning of a rational exponent. And rational exponents is just what it sounds like. A rational number is a fraction. So now we're getting our first look where bases have exponents that are fractions. And of course, m and n, numerator and denominator, need to be integers. Remember that you can't have 0 in the denominator of any fraction. And b in this case needs to be a positive real number. So that's looking at the definition, and let's investigate that a little bit more clearly and a little bit further. This says that a fraction exponent or a rational exponent is the same as taking a radical. And here's how we kind of twist it around. There's two choices of how you can rewrite it. And in some situations, one choice will be better. In some situations, the other choice will be better. But b, the base, becomes the radicand. Remember, the radicand is the number under the radical sign. The denominator of this rational exponent is the root index. So that goes in this little portion of the radical sign. That's the root index. The numerator is the power that is being raised to. So we can either take the nth root of b first and then raise it to the m power, or we could take b, raise it to the m power, and then take its nth root. You have a choice. And so what we want to do to make that a little bit easier to understand is look at a numerical example. And eventually you need to get good at this so you can do this in your head and say the answer is 9 without really writing much down. You can be able to figure this out. But let's look at a couple of different approaches. So the first solution is, let's write it this first way. Let's say we're going to take the cube root of 27. So 27, the base, becomes the radicand. The denominator becomes the root index. The numerator is the power we're raising that to. And this one looks fairly easy. Then we're going to take the cube root of 27. Yes, you still need to know your perfect squares, perfect cubes, perfect fourths that I asked you to know earlier. And so the cube root of 27 is 3. We're going to take that and square it, and my answer is 9. And so that's one approach, and actually that's, in this example, that's the first definition, and that is much easier than the second solution. Second solution says we can write it in this other notation, which says 27 is still the radicand, but we're going to take 27 and square it first, and then we're going to take its cube root. Well, that gives us some bigger numbers, and you may or may not have memorized your perfect cubes that far. 27 squared is 729. Now it's obvious because we just did this that the cube root of 729 is 9, but you may or may not have that memorized. So in some cases it'll be preferable to rewrite it in this first format. In other cases it may be preferable to write it in the second format. Alright, let's look at another numerical example so we can get used to this. So 64 to the negative 3/2 power. We're going to be combining our properties of exponents. And the first thing I would suggest is that a negative exponent means take the reciprocal of the base. So this is 1 over 64 raised to the positive 3/2 power. And realize that 64 is my radicand, 2 is my root index, so it's a square root, and then I'm going to raise that to the 3rd power. Simplifying that as we go, the square root of 64 is 8. 8 cubed is 512, and my answer is 1 over 512. Let's look at another one, because eventually we need to also remember that rational numbers could be written as decimals as well as fractions. So 16 to the 2.5 power. Why don't we now look at 2.5 as a fraction? 2.5 is the same as 5/2. So we want 16 to the 5/2 power. So 16 is my radicand, 2 is my root index, so it's a square root, and then we're going to raise that result to the 5th power. Square root of 16 is 4. 4 to the 5th power is 1024. But eventually we need to get good at this, so you can do this in your head. Now those were nice, easy numerical examples so we can practice the property of negative exponents that we're learning. But here's a more abstract one, because there's no numbers here, all variables, and we want to be able to write radical notation in exponential notation and vice versa. So in this case, let's take the radicand, and going backwards, that's going to be the base. The root index is the denominator of the fraction I'm raising to, and I can think of this entire radicand as being raised to the 1st power. Now we need to recall those properties of exponents that I just reviewed at the beginning of this lecture. We have a fraction raised to a power. We raise the numerator, raise the denominator. As we do that, the numerator, we have a product. So let's take x to the 7th power to the 1/3 power. Remember, when you have a power raised to a power, you multiply. 7 times 1/3 is 7/3. Y to the 5th to the 1/3 power, 5 times 1/3 is 5/3. Z squared to the 1/3 power, and the denominator is z to the 2/3 power. And the last thing it says, write an exponential form, which is essentially saying we can't have a denominator that has a fraction exponent. Because really a fraction exponent is a radical in disguise. This is saying the cube root of z and then square it. And we couldn't leave a radical in the denominator when we studied our chapter on radicals. So in this case, they would like us to use negative exponents. So we're going to take that z to the 2/3 power and write that as z to the negative 2/3 power, which is the reciprocal. So all we're doing is practicing that property forwards and backwards. All right, let's put some more numbers in and see what we can do with this one. This one's interesting because we have radicals and fraction exponents all in the same problem. But I would suggest that we start by dealing with this negative exponent. Negative exponent means take the reciprocal of the base. So instead of 1 over the cube root of 9, that's the cube root of 9, and now it's raised to the positive 3/2 power. After that, I would suggest let's rewrite this radical as a fraction, or a base raised to a rational exponent. The radicand is my base. The root index is my denominator, and inside the parentheses, nothing's being raised to any power, so let's call that the 1st power. And now we have a base raised to a power, which is in turn raised to another power, and we multiply. 1 over 3 times 3 over 2, you can see that the 3's reduce and leave me 1/2. 9 to the 1/2 power. You need to get good at this. That's another way of saying what is the square root of 9. My base is my radicand. Denominator, root index. Numerator is the power I'm raising that to. And of course, we all know that the square root of 9 is 3. All right, let's look at another example. In our chapter on radicals, we said this could not be simplified. And that was true with what we knew then, but not true with what we know now. Back then in the chapter on radicals, you said you couldn't multiply radicals unless the root indices were the same. This is a square root, that's a cube root, they're not the same, we couldn't multiply them. However, now that we know rational exponents, let's try getting rid of the radicals and writing 8, my radicand is the base, it's a square root, so my root index is 2, and that's being raised to the first power. This radicand 4 is my base, the root index is 3, that's the denominator, it's being raised to the first power, that's my numerator. And we know that 8 is 2 to the third power. We know that 4 is 2 to the second power. So let's take those and simplify those a little bit more. We have a base raised to a power, raised to a power. We multiply those powers. 3 times 1/2 is 3/2. 2 raised to the second power, raised to the 1/3 power, excuse me, when we multiply is 2 to the 2/3 power. And I hope you can see now why I rewrote 8 and 4, because I realized 8 and 4 are both powers of 2. Because now we're multiplying and the bases are the same, we can keep the base and add the exponents. 3/2 plus 2/3. Of course, we'll need a common denominator for that, and 6 would be the common denominator. 3/2 is the same as 9/6. 2/3 is the same as 4/6. And when we add those now, we get 2 to the 13/6 power, which I'm going to suggest we write that as a mixed number exponent instead of an improper fraction exponent. 6 will divide into 13 2 times with 1 left over. 13/6 is 2 1/6. And if we do that, we can break that down and say that's 2 squared times 2 to the 1/6 power. And we're going backwards on this one. If you're not sure of that, let's kind of go forwards. If you were multiplying, the bases are the same, you would keep the base and add the exponents. 2 plus 1/6 is 2 1/6. So if we have it as a mixed fraction rational exponent, we can split it back to 2 to the whole number portion times 2 to the fraction portion. And if we do that, 2 squared is 4. And let's put this back as a radical. The base is the radicand. The denominator is the root index. And we're raising that to the first power. And so what we thought was impossible when we did our lecture on radicals, we could not then multiply radicals that didn't have the same root index. Now with rational exponents, we can simplify them. Square root of 8 times the cube root of 4 is 4 times the 6th root of 2. Well, typically when we learn something new, we'll play with some numbers and work on that, and then we'll start solving some equations. So this is an exponential equation where my exponent is, of course, a rational exponent. And what I want to do is I would like to get rid of that exponent. And the way to do that is to raise both sides of the equation to a power. What power? Well, I would suggest the reciprocal. Because remember the multiplication property of identity. When you multiply reciprocals, you'll get 1. So if x minus 1 is raised to the 3/2 power, I'm not multiplying, but I'm raising both sides of the equation to the 2/3 power. On the left, what that does, I have a base raised to a power, raised to a power. I multiply those. That gives me 6/6, which is just 1. And I'm left with x minus 1. Now, I suggested that we learn how to do this in our head, and I did that. So let me explain what I did in my head. This says find the cube root of 8. Well, that's 2. Take that result and square it. Well, that's 4. Solve for x, add to 1 both sides, and we've got our answer, x equals 5. Let's look at solving another equation that's exponential in nature, and its exponent is a rational exponent. I would suggest in this case, let's get the variable by itself first. Divide both sides of the equation by 5, and that gives me x to the 1/3 power equals 4. Next, I would suggest raising both sides of the equation to some power that will give me x to the first power on the left. And of course, I'm going to use my property of reciprocals. If I multiply 1/3 times 3, that will give me 1. And of course, negative times negative is positive. But be careful, I am not multiplying both sides of the equation by -3. I am raising both sides of the equation to the -3rd power. So on the left side, a base raised to a power, we multiply those powers and we get x to the first power. Positive first power, that's what we would like. On the right, negative exponent means take the reciprocal, so that's 1/4 to the third. And then if we simplify that, 4 times 4 is 16 times 4 is 64. So x is 1/64. And that's our first look at using rational exponents.